Hello guys, welcome back to MJ School of Mining and Geology. In today's session, we are dealing with the characteristics of a periodic table. So as a geochemist or as a chemist, you need to understand, for you to be able to understand the chemical reactions, you need to understand the periodic table. Basically, periodic table is a systematic arrangement of elements based on their atomic number. And atomic number represent the number of the protons based within the atom, or based within the nucleus of an atom. So please don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload the new content. So basically, like I said, the periodic table of an element, okay, it's a table of the known chemical elements arranged in the order of atomic number. The modern periodic table of elements is based on the work of the Russian chemist Dmitry Mendeleev, and it is arranged by the atomic number, which is just the number of the protons. This reflects the number of protons in the nucleus of an atom. So you would agree with me that an atom is the building block of matter, and the atom is divided into the nucleus, and the orbital shells. Okay, orbital shells. So what's in the nucleus? What's in the nucleus is protons and neutrons. Neutrons, they don't have a charge. Protons, they have a charge. But if you combine these protons and neutrons, they're gonna give you the atomic mass number, or they're gonna give you mass number. They're gonna give you a mass number A. And then, but only the number of protons, which is Z, they're gonna give you the what you call it, the atomic number, which is the number of protons. And we know that when we want to calculate the number of neutrons, the number of neutrons, it will be A minus Z. So you take the what's in the nucleus, and then you minus only the protons. What's in the nucleus is the number of protons and neutrons, and you subtract the number of protons. So then the periodic table, it's the systematic arrangement of the elements based on their atomic number, or the number of protons. And it was compiled by the Russian chemist known as Dmitry Mendeleev. Okay, so basically that is that, and we're gonna learn more about the periodic table today. Moving right on. Sorry about that. Moving right on. Okay, so this is what is called the periodic table, and I know that most of you know this. And this periodic table is divided into groups and into periods. All right, so periods are the horizontal rows in the periodic table. All right, the horizontal rows are one. If you can check, they are these ones. Let me do this. Rows are these ones: 1, 2, 3, 4, 5, 6, 7. Sorry, these are rows and or periods. These are the horizontal rows in the periodic table. Okay, and then we've got 7 of them, and then each row, it corresponds to addition of the electron shell around the atom. So it means if this is the nucleus, for example, let me just make for row 1, 2, 3. All right, for row 1, if this is the nucleus, you'll have only one shell. For row 2, you'd have 2 shells. Then row 3, you'd have 3 shells. So each row, it corresponds to the addition of a new electron shell around the atom as you move down the table. So I hope this makes sense. But now, what we should ask ourselves is, Why the chemical properties change across the period? All right. This is because as you move down from here, from the top, okay, to bottom, okay, as you move, but no. All right. Let me start by saying why the chemical properties change across the period, all right? When you are moving from here to there to there, sorry, there to there, all right? Why that? As you move from left to the right across a given period, all right, the atomic number of the element increases. So if the atomic number of the element increases, it means you are increasing the nuclear charge. It means you are increasing the charges within the nucleus. So if this is the nucleus, all right, you are increasing the charges, the number of charges within the nucleus. You're increasing the number of charges within the nucleus. What are you doing? But because we know, according to the laws of chemistry, that the unlike charges, they attract each other. We know that the positive will attract the negative. So, because you are increasing the number of the positives in the nucleus, you are forcing the electrons in the orbital shells, the number of electrons in the orbital shell, to be strongly attracted, to be brought closer to the nucleus, because you are increasing the nuclear charge. So, which is why when you are moving from left to right, all right, you are increasing the atomic number. That is to say, you are increasing the number of protons or the number of positives. All right. So if you're increasing the number of positives, okay, you are basically adding, or the electrons are going to be added to the same electron shell or the energy level. All right. So, which is why the number of protons, when they are increasing, the nucleus will pull the electrons more strongly, which affects the various properties like atomic size, the ionization energy, the electron affinity, and the electronegativity. So now let's learn about the trends for the given period. All right, let's learn about the trends. So we're gonna be looking at the atomic size. And we're gonna look at the ionization energy, and also the affinity, and other things. All right. But now let's start with the atomic size. Let's start with the atomic size. So today we're gonna look at the atomic size, and then we're gonna also look at what we call it the ionization energy. We're gonna also look at the electronegativity. We're also gonna look at the reactivity. We also look at the affinity, the affinity. Okay. So we can start with what you call the electron affinity. So basically, the electron affinity is the energy change that happens when an atom gains an electron. All right, is the energy that happens energy change that happens when the electron gains an electron. So let me give you an example. Imagine if you are having the magnet and the metal a paper clip. Some magnets strongly pull the paper clip, while others they barely attract that. All right. So this would have the same analogy as these things. Let me give you example of the example with the chlorine. All right, and something in the last group, which is what we call the noble gases. Let me give you, maybe, let's say, what you call it, the neon. Let me just give you example of the neon in the last group. All right. So we know these ones, the halogens, they need one electron for them to reach their octet stage, to be happy and to feel comfortable. But the ones in the neon, it does not need any electron. All right. So chlorine would love to gain an electron because it helps it achieve a stable state, just like filling the last seat in a bus row. All right. But if we were to look at so when we're looking at this chlorine would love to gain an electron. But now as it gains electron, it releases more energy. All right? It will release more energy, making it more stable. But if we are looking at the noble gases like neon, argon, and others, okay, they are inert. They reach their octet state. All right, they reach their octet state. It means they do not want any extra electrons because they are already comfortable, like a full bus with no empty state. Okay, so this means electron affinity. It will tell us much about how much an atom like gaining electrons, with some elements releasing energy or releasing more energy when they accept one, okay, like chlorine, while others barely care or even resist to gain the electron. So this is what we call the electron affinity. But with the atomic size, ne? So atomic size is the distance from the nucleus of an atom to the outermost shell of an electron. The distance from the nucleus of an atom to the outermost shell. So that is to say, if ever this is the, okay, the distance is the distance from the nucleus. If this is the distance, let's say this is that. Okay. So it will be the distance from this nucleus all the way to there. So it means if you are increasing more positives in the nucleus, you are forcing this thing, the outer or the electrons to be attracted to. It's like they're shrinking because they're going to be they're going to be held tightly. All right. So that is that. So it will mean the atomic radar, it is essential to measure the size of an atom. All right, that is atomic size. But what about the ionization energy? The ionization energy is the, how can I put it? It's the amount of energy required to move an electron from an atom in the gas phase. So it means it's just nothing but the measure of how tightly an atom holds onto the outermost electron. That is what we call the ionization energy. But when we talk about the electronegativity, it's nothing but the ability of an atom to attract electrons in the chemical bond. The ability of an electron to attract the ability of an atom to attract electrons during the chemical bonding. And then the reactivity refers to how easily an element can undergo a chemical reaction with other elements or compounds. For example, if we were to look at the difference between metals and non-metals, you would agree with me that the metals, this usually means how is with the metals. When we're talking reactivity with metals, it's how easily they lose electrons. But with non-metals, it means how easily they gain or share electrons. So basically, these are the terms. So now we're gonna be, if you understand these terms, we're gonna now be looking at the trends, okay, across the period. We're going to now be looking at the trends across the period. So let's start with the atomic size. So atomic size will increase from left to right. So it means as the nuclear charge increases, the electrons are drawn closer to the nucleus. Now, this will make the atoms to become smaller, because remember I told you that the atomic size, it tells us much about the size of an atom. All right. But now, with respect to ionization energy across the periods, it will increase from left to right. It means more energy is required to move an electron. Okay, because the nucleus is becoming more positively charged and holds electron tightly. So if the electrons are held tightly, it means you're gonna require more energy to move at least that electrons, because they are tightly held closer to the nucleus. So you're gonna require more energy to be able to remove them. But now the electron affinity, it will become more negative from left to right. This is because atoms more readily accept an electron as the nuclear charge increases and pulls and pulls electrons in a stronger fashion. Okay. Then electronegativity, it would increase from left to right. It means the ability of an electron to attract electrons, the ability of an atom to attract electrons, it will increase from left to right. It means elements toward the right-hand side, like fluorine, chlorine, bromine, and iodine, they would have they are more electronegative as compared to elements on the left hand side like sodium, lithium. So the element towards your left they are less electronegative as compared to the more electronegative elements like fluorine and chlorine. It means chlorine and the fluorine, they are attracting electrons more. They are attracting electrons more. For example, that's why I told you that the group seven ones, like chlorine, they are comfortable when they are attracting one electron. Okay, which is why when I give you example, if I can give you example with sodium and chlorine. Okay, when I give you example with sodium and chlorine. Okay, sodium and chlorine in period in period 3. Okay, in period 3. They are all in period 3. Okay, from left, the other one is on the left hand side, the other one is toward the right hand side. Okay, remember we are looking at the period. So if you were to consider the sodium and chlorine in period 3, sodium has a low ionization energy, for example. Why? Because it will lose its outer electron easily. All right, it will lose its outer electron easily. Because of the positive charges, they are not strong. So it means the electrons, they are not tightly held. But towards the right-hand side, the chlorine, okay, because of when you are moving towards the right, you are having the nuclear charge increases. It means now that it's going to be difficult for chlorine to lose one electron. Okay, it will be very difficult for chlorine to lose electron because it has got high electron affinity. Okay, and readily gains an electron to form a stable negative ion. I hope you understand that the sodium has a low ionization energy and loses its outermost electron easily, while the chlorine has a high electron affinity and readily gains an electron to form a stable negative ion. I hope this makes sense. This is when we are still looking at what we call the still looking at what we call the P rod. Okay, and we looked at the trends as well. All right. So, but when we're looking at the groups, okay, so the groups are just the vertical columns. Okay, and then we've got when we're looking at the vertical columns, we've got 18 of them. Let's count them. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We've got 18. And then these ones at the center, we call them the transition ones. Okay, we call them the transition ones. So then we've got these ones, and then this ones is group 1, group 2, group 3, group 4, 5, 6, 7, 8. So group 1, these groups, they tell us basically what's happening is the groups, they share the similar chemical and physical properties. So it means the group ones, such as hydrogen, lithium, sodium, and so on, they share the same chemical and physical properties. And the beryllium, magnesium, calcium, and many others, they share the same chemical and physical properties. Okay, so we are asking ourselves why elements in the same group behave similarly. This is because the elements in each group have the same number of valence electrons. So for group 1s, they've got 1 valence electrons. In the group 2, they've got 2 valence electrons. In group 3, they've got 3 valence electrons. In group 4, they've got 4 valence electrons. In group 5, they've got 5 valence electrons. In group 6, 6. In group 7, they've got 7 valence electrons. And in group 8, they've got 8 valence electrons, and they reach their octet state. Then the group 8, they've got 8 valence electrons. The exception it will only be what we call it the helium. Helium, it has got two valence electrons, but it is happy and it is comfortable. It reached its octet state with only these two. These are the exceptions. And the exception in group one is what we call the hydrogen, because hydrogen can lose one electron and can also even gain one electron. So these are the only two exceptions. Okay. So let's look at the traits. So when we are looking at group ones, which we call them alkali, which group ones, we call them alkali metals, all right? Which is why when we're looking at feldspars, when we're looking at alkali feldspars, they've got two end members, sodium and potassium. So which is why we call these things in group one alkali metals, all right? So these elements, we're talking lithium, we're talking sodium, potassium, they have we are talking lithium, sodium, potassium, okay, and all have one electron in their outermost shell. All right, so making them highly reactive, especially when it comes to water. So they're highly reactive with water. So it means their reactivity increases as you move down the group. It means potassium, it will react more with water as compared to lithium. But when we're looking at group 17 or group 7, okay, what we call the halogens, okay, like fluorine, chlorine, iodine, okay, they have 7 valence electrons, as I've explained. This makes them highly reactive, particularly forming salts by gaining one electron to fill their outer shell. So their reactivity decreases down the group. It means the fluorine and chlorine, they will be highly reactive as compared to iodine, all right? Iodine, because of their reactivity decreases down the group. But when we're looking at the noble gases, for example, group 18 or group 8, these elements like helium, neon, argon have 8 valence electrons, making them chemically stable and largely unreactive because it's like they are full and they reach their octet state. They are happy, they are comfortable. You cannot eat while you are full. So these elements, they've eaten, they are full, and they cannot need other food. So they are fine. All right. So, for example, let me give you an example with magnesium in group 2 and this magnesium in group 2 and the calcium, all right? And the calcium, looking at one group, all right? So magnesium in group 2 and calcium in group 2, they behave similarly because both have 2 valence electrons. Remember, we said things in the same group, they would have they will behave, or they would have the same physical and chemical properties. Okay, so the both of these things, because they belong to group 2, they would have 2 valence electrons. So these elements readily lose their valence electron to form 2 ions. But calcium is more reactive than magnesium because its valence electrons are further from the nucleus and more easily lost. Remember, I told you that the more you are going down, the more you are adding the outer shell. So the calcium, all right, you've added another shell as compared to this one. So this one, as compared to calcium, the calcium is like you've added another shell. So that addition of another shell, although they are from the same group, the addition of another shell for calcium, it makes it more reactive than magnesium. Okay, because now the valence shell, or the valence electrons of this calcium, it will be further away from the nucleus. So if it's further away from the nucleus, it's going to be more easily lost because of there is no strong attraction and the positive charges in the nucleus. Okay, I hope this makes sense. I hope this makes sense. So basically that is that. Basically that is that. So looking at the periodicity, the repeating pattern of the properties. Okay, so when you are looking down the group, okay, remember In terms of the atomic radius, when we're looking across the period, when we're moving from left to right, all right, now we are looking or we're moving from top to bottom. So the atomic radius, it will increase from top to bottom, okay? Because you are adding, always when you're going down, you are adding another new shell. So when you are adding another new shell, it's like now you are moving far away from the nucleus. And remember, what is atomic radius? At the distance from the from the nucleus to the outer shell. Okay. So because you are, this is because why the atomic radius increase is because with each new period, a new electron shell is added. So the outermost electrons are further from the nucleus. But now, in terms of the ionization energy, from top to bottom, all right, the ionization energy decreases because the outer electrons are further from the nucleus and experience less attraction. All right, it will experience less attraction because the positive, the nuclear charge, the electrons is like they're not feeling that strong attraction. Yeah, the positive because of the positive in the nucleus because you are far away from the nucleus. That's why the ionization energy it will the soil ionization energy, it will decrease down the group. But when we're looking at the electronegativity, okay, down the group, the electronegativity will also decrease because the outermost electrons are what? Are further from the nucleus and are less attracted to the other atoms. So, and then when we're talking the reactivity, okay, for example, when we're talking about the reactivity, for example, for alkali metals in the group one, the reactivity increases as you go down the group. The reactivity, like I've mentioned, that the potassium it will be more reactive than the lithium. The reactivity it will increase down the group. Okay, when you're looking at the group, at group one or the alkali metals, the reactivity it will increase as you're going down the group. Potassium and this cesium, okay, the more they are more reactive. The potassium and this cesium and or this one, they will be more reactive. They will be more reactive than the lithium because lithium is up there. All right. But when we're looking at, for example, at the halogens of group 17 or group 7, the halogens with one electrons in their outermost shell, the reactivity will decreases as you go down the group. Fluorine is highly reactive. Fluorine is highly reactive. All right. While the iodine is less reactive, which is why we are saying the reactivity decreases as you're going down the group. So the ones at the top, they are more reactive as compared to the ones at the bottom. So I hope these ones, they make sense. Okay. So, characteristics of the periodic table. The periodic table is organized like a big grid with rows running left to right and columns running from top to bottom. And up to so far, we've looked at the traits. Each element is placed in a specific place on the grid because of the way it behaves. This in turn has to do with its chemical properties. Its chemical properties. Sorry. Each of the rows each of the rows is a different period. Element in the same rows, they've got the same chemical properties and the physical properties. All right, because of they have they have the same number of, or they've got the same electrons in their outermost. So for group one, they will have one electron. For group two, they will have two electrons. But for group one, hydrogen is the exception. But in the group 8 or in the group 18 with neon, it will be the helium, it will be the exception. Okay. All of the elements in a period have the same number of atomic orbitals. Okay. Every element in the top row, the first period, has one orbital of its electrons. I've already explained that. All of the elements in the second row, they would have two electrons in their outer shells. The maximum number of electrons orbitals or electron shells for any element is 7. Okay. the maximum number of electron orbitals, because we've got seven of the periods, and it makes sense that when you are going down, you are adding another orbital shell until number seven. Then the number seven, it will be the last orbital, right? It means you cannot have orbital more than seven. You cannot have eight orbitals. Every element in the first column, group one, has one electron in its outer shell, and then number two, it will have two. Number three, it will have three. Every element on the second, like I said, it will have two, and so on and so on. So, like I said, with the exception, hydrogen and helium, there are the exceptions because the hydrogen can miss an electron, and sometimes it can have an extra one. But helium, although it's sitting in the group 18 with everything having, or group 8 with everything reaching their octet state, being happy, being inert and unreactive, this helium, it is happy with only two electrons in its outermost. It reaches its octet, it octet stage like that. Its octet state like that. So the elements in the center section are called transition elements and have their special electron roles. So in the end, we've already talked about these periodic trends in details. So we've talked about the atomic radius increasing from left to right, but decreasing from top to bottom. We've also talked about ionization energy increasing from left to right, but decreasing from top to bottom, and so on and so on. So this brings us to the end of the characteristics of the periodic table. This periodic table is very important to be understood by chemists and also by a geologist or a geochemist, because for you to understand how elements or minerals behave, you need to understand the periodic table. You need to understand where they stay, how they behave, and many other things. You need to understand their physical and chemical properties. All right. For other people like mineralogists, okay, for you to understand the physical and chemical properties of minerals, you also need to have the background of what's happening with periodic tables. So, good people, don't forget to like and share and comment. But above all, do not forget to hit the notification button below so that you get notified once we upload new content. Thank you guys for joining us today. It really means a lot to us. I always like to say, until next time, cheers.